Okay, and it's 5 past. We were very pleased to have Harald, who was once a member of our department, and he will be telling us today about the expander hierarchy and its application in dynamic graph algorithms. Please, Harald.
Yeah, thanks a lot, and thanks for inviting me. Unfortunately, I could not really visit Warwick again because of this stupid pandemic. Okay, so this is joined with Gamos Guanci, Sachapol Saranovac, and Xian Tan. And what is the topic? In some sense, the topic is about tree-cut sparsifiers. So because we'll see that this expander hierarchy that I will define later in the talk will be a tree-cut sparsifier. So what is a tree-cut sparsifier? So in this setting, we are given an undirected graph, and the graph is could be weighted, but in this talk, I will assume that it's unweighted. And in what we want to do is we want...
Harry, we don't see the slides.
You don't see the slides. Why don't you see the slides?
I don't know.
I actually see the slides.
I can see the slide too.
But only the first slide.
Only first.
Only the first slide. Only the first slide. Okay.
And I'm assuming, are you, Harry, on the first slide or not?
No,
yeah, we see the first slide, but he shouldn't be in the first slide. So I guess, right?
No, I'm not.
Sometimes it helps if you exit.
So I stop. I start again. Like this. So do you see the first slide?
Yes.
Yeah.
Do you see the second slide?
Yes.
Yes.
Oh, okay, let's try.
Okay.
Okay, I want to talk about tree-cut sparsifiers. So you're given an undirected graph, and I assume for this talk that it is unweighted. And what you want to do is you want to compute a tree. The tree has a larger vertex set. So the vertex set on the tree contains all the vertices of the graph, but may contain additional vertices. And you want the tree to approximate the cuts in G. So what does it mean to approximate the cuts in G? Suppose that I take a set of vertices, and now I look at the corresponding cut in G, and this kind of should denote the capacity of the cut, the total capacity of all edges that cause a cut. So the weight of an edge is the capacity. And now I want that the corresponding cut in the tree is kind of larger, and it's not too much larger. So what does it mean, the corresponding cut in the tree? So in the all vertices in S, they also exist in the tree, and the vertices in V minus S, they also exist in T. In T may have additional vertices, but now I look at the min cut that separates the vertices from S and the vertices from V minus S. I look at the min cut that separates these, and this I denote with this value, and then I want that the min cut in T is at least the size of the cut in G, and at most, so if I divide the cut in T by Q, then this should be smaller than the cut size. So kind of this gives this approximation, and the approximation factor is Q, which is called the quality of this approximation. So here a picture. So what I do is, if I look at the cut here in this graph, then in the tree here, I have the leaf vertices. They correspond to the vertices in the graph. May not necessarily be the case that these are the leaf vertices, but for our sparsifiers that we are looking at, these will be the leaf vertices. And then I mark these guys that are here. I mark them, these are the red vertices, and then in the tree, I compute a cut, a min cut between the red vertices and the blue leaf vertices. Maybe I decide, oh, I take this edge out, I take this edge out and this edge out, and then I still have a connection here, so maybe I'm taking this edge out as well, and then I'm cutting at least the blue vertices in the from the get vertices, and this would be a cut, and then I would compute the min cut. So why are we interested in tree cut Sparsifiers? Because they are very good for solving complicated problems that have to do with cuts. Any kind of cut-related problem I can solve on the tree, and then I can kind of transfer the solution to G, and I get an approximate answer. So, for example, for minimum bisection, simultaneous source location, K multicut. So there are a lot of cut problems where this has been done, and where this is kind of sometimes even gives the best results that exist for this problem. And the main strength from this comes that on the tree I can solve problems very often by using dynamic programming, and so I get a very good solution on the tree, whereas on the graph I usually don't have dynamic programming approaches available. So, and now what kind of constructions exist there? So again, goes a little bit through the previous work. I've worked a lot on this problem. So here I also have the concept of a flow Sparsifier. Flow Sparsifier is slightly different. It says any flow that I can route in the tree, I should be able to route in the graph with approximately the same congestion. So this is a flow Sparsifier, and flow Sparsifier is strictly stronger than a cut Sparsifier, but the difference is at most a logarithmic factor because of the approximate maximum cut ratio. So these are closely related, and as we've seen in our talk, logarithmic factors will not be important for us. So here's the first paper showed the existence of such a structure, of such a tree cut Sparsifier, and it gave a quality of log cubed n. And subsequently in these papers, this has been made, not really efficient, but there were polynomial time constructions given. And the first paper then gave a weaker approximation guarantee, and then this paper here even improved the approximation guarantee from the log cubed n. In this paper, kind of the difference between flow and cut Sparsifiers was exploited. Kind of the question was asked, if I just want to, if I don't want to have the guarantee of a flow Sparsifier, but just a guarantee of a cut Sparsifier, can I kind of improve the guarantees? And one could shave off a little bit here in the exponent. And it was shown that actually existentially, there is always such a cut Sparsifier that guarantees the quality of log n times log n. And there's also a lower bound for this. So the lower bound stands at log n, so there's a slight gap between what I can obtain here. And in this paper, we showed that we can actually compute such a cut Sparsifier fairly efficiently. We can compute it in nearly linear time. So we have fast constructions for these cut Sparsifiers. And now, what is the topic in this paper? In this paper, the main result is a dynamic construction of such a tree cut Sparsifier that has an up. So what we do is we make this whole thing dynamic. So if we have edge insertions and deletions, we want to maintain such a cut Sparsifier. We do not want to compute it from scratch. And what we show is we can obtain something like this with an update time of n to the little of 1. So what is n to the little of 1? We have something like, okay, we have, and the whole result will be a little worse, but we have something like 2 to the squared log n. Roughly looks like this. So this is, as an update time, this is kind of fairly okay. Unfortunately, we do not have a polyrhythmic guarantee anymore. So the guarantee will not be kind of log to the 4n or something like that. It will be n to the little of 1. So it will not be polyrhythmic, and this is kind of the disadvantage of this paper. But apart from this, so it ticks all the boxes that you want to tick in dynamic graph algorithms. It's fully dynamic, so it's supports insertions of edges and deletions of edges, and it's deterministic. So this is also sometimes very important in these dynamic graph algorithms. And then, of course, what is usually standard, what can be done very often, if you have an amortized result, you can de-amortize it, so you can also de-amortize it, that you don't have an amortized guarantee. So what we show in the paper is kind of, we show that these as amortized guarantees, where on a long period of updates, the update time is for k updates is k times n to the little of 1. But then you can de-amortize it. That's for every update you just spend this time. Okay, so now I want to go a little bit into describing how a variant of the previous proof techniques works to get a result, and how we kind of then use this. And in the end, I will talk a little bit about how to make this dynamic. So in particular, what I want to explain where this n to the little of 1 comes from. And for this, I have to kind of elaborate on the way how you prove the guarantees. And now I see that I forgot something. I want to talk about the consequences for dynamic graph algorithms. Okay, these are applications of all of this. And the applications are not very insightful there. Sometimes they are trivial. This simply comes from the power of this tree cut sparsifier. And for example, if you look at connectivity, you ask, are you connected? Now, if you give it a tree cut sparsifier and the tree contains a path between S and T, then S and T will be connected. So if I ask ST connectivity, I can do this. If I ask connectivity, I just have to check whether this tree whether there are two components in there or not. And I can do this all very efficiently. If I want to ask what is an ST max flow min cut, so I want to maintain an ST max flow, what I do is I maintain this tree, and then I have to ask, if I get a query, what is maximum flow between S and T, I have to solve this problem in the tree. Actually, what we will see is the tree that we construct has logarithmic diameter. And then, of course, in a tree with logarithmic diameter, I look at the path between S and T, and then I can determine the max flow in the tree. And therefore, I can solve this problem. So update time for constructing the tree, this will be the approximation that I get. And this is the time for computing the max flow. So, and all these applications here kind of, there were no real trivial bounds and no non-trivial bounds known before. So these are consequences for dynamic graph algorithms. But the real problem with this, the approximations are all n to the little of 1, and ideally one would like to have something better. But you will see that maybe using this approach, this might not be that easy. Okay, how do existing proofs work? So first of all, the existing constructions for a single tree. Oh, maybe I forgot something. So I forgot to highlight one thing here. This is for unweighted graphs. The concept of a tree cut sparsifier exists for weighted graphs, of course, and also previous constructions, they also work for weighted graphs. Here, the dynamic constructions, it's a little bit difficult. At least our techniques kind of don't carry over to weighted graphs. And it seems a little bit difficult because if you kind of suddenly add an edge with huge weight somewhere, you can kind of change the graph quite dramatically. So it may really mean that doing it for weighted graphs, it's more challenging. So here for the dynamic construction, we really need unweighted graphs. So this is kind of important note to this main result. So previous approaches kind of looks, the tree looks like this. The tree always has the leaf vertices of the graph. The leaf vertices of the tree represent the vertices in the graph. This is one point. And if I have something like this, then if I look at the level here, level in the tree, this kind of induces a partitioning of the vertices into subsets. So here I have the subset ABC, this is one subset, I have this subset, there's this subset. So, and then I have a subset for this vertex that contains all the vertices. So the tree kind of forms this laminar family. And now if I'm given this tree, the existing approaches and also our approach kind of assigns the capacity of the tree edges in a very standard way. Namely, what you do is the following. An edge in the tree is assigned a capacity that is equal to the capacity of the corresponding cut in the graph. So if I take an edge here in the tree and I ask, what capacity should this tree edge have? Okay, so here I look at the corresponding cut that it induces. So this induces a cut in the graph. So the cut is here. And now I would assign, there are 4 edges going over the cut. I assume that the graph is unweighted. So every edge has weight 1. So I would assign 4 as the capacity of this tree edge, the number of edges that go across this cut. There's another way to view this. I could also view it in the following way. Every graph edge contributes to the capacity of every tree edge on the path between its endpoints in T. So what does this mean? I say I take a graph edge, and now I'm looking at the corresponding path in the tree. So I'm here, this is the kind of this graph edge. And now I say, oh, this graph edge will add 1 to the capacity for every tree edge on its path. And I do this for every graph edge. So then I take this graph edge here. This is between these 2 edges. For this graph edge, I increase 1 for every edge on this path. And then I can do this also with this okay, I have to see whether this graph edge is available. I can also do it with this graph edge. So I add +1 here, and now I get 2 here. I get a +1 here and a +1 here. So these would also already have a capacity of 2 and so on. So this is kind of the same assignment as before. And now if I do the standard assignment, I already get the guarantee that the cuts in the tree always dominate the cuts in the graph. So claim, this is one direction that we have to show. The cuts in the tree should be larger than the cuts in the graph. And why is this true? Suppose that I take some cut here in the graph. So this says, oh, I have these vertices on one side. And now in the tree, I will compute a cut between the red leaf vertices and the blue leaf vertices. And now I ask, if I take an edge here, I take this edge, and it contributes to the capacity of the cut in the graph. Does it also compute to the capacity of the cut in the tree? I don't really know the cut in the tree. But I know that this graph edge contributes to the capacity on every edge on its path. But this is an edge here that connects a red leaf vertex with a blue leaf vertex, because it's kind of an edge of the cut in the graph. But the tree, of course, the tree cut has to kind of remove one of these edges. Therefore, the kind of the yellow edge will, its capacity will also contribute to one of the edges that the tree cut has to take out. And therefore, the cuts in the tree are always larger. So this is kind of one direction that one shows. So this is kind of one direction. And the important thing is usually to show the other direction. So how do you show the other direction? I said that if I take one level of this tree, then it partitions is kind of a vertex partitioning. So and now I take the ice level. Level 0 is a leaf level. So levels go up as I go up in the tree. So this is some level I partitioning. And now I use this to denote the contracted graph. So what I do is I have a partitioning, and every vertex set in this partitioning, I contract everything into a single vertex. And this gives me a new graph. All edges that are between vertices of the same component, they kind of disappear, and only the other edges remain. So this is a contraction. And now I want to have the following two properties. First of all, suppose that I have a cluster S on some level I+1. So basically in my tree, this is a subset on level I+1. And now what I do is, I will formally explain this in notation in a moment. I want to view this kind of as an induced graph in the, this is kind of something like the induced graph on S. So I take G of S, and then I contract all subsets that are one level down. These subsets are contracted, and this gives me some contracted graph, and I want that this graph expands well. This is the first property that I want. And then what is the second property? I want that the set S should have good boundary expansion. And I will explain this now in more detail. So these are two properties that I want. So what does boundary expansion and what does here expand well mean? So here is this cluster. This is the set S, and now these are the kind of the clusters that this is partitioned in, because I have this laminar family of partitions. So these are the clusters on the next level. So what does the first property tell me? The first property tells me, so here are some edges. So there's some cluster in this graph. Some edges may actually go out here. So now what is this graph? It's actually not the induced subgraph. Okay, sorry. What is this graph? It's not the induced subgraph, but what I do is I take the induced subgraph, but in addition, for every vertex that is here at the boundary, for every boundary edge, I will create a self-loop here. Here I will create a self-loop for each of these boundary edges, and here I will create two self-loops. So the vertices that are at the boundary, for every boundary edge, they get a self-loop. So in some sense, the number of edges doesn't really go down. So this is, these curly braces mean that kind of I am adding self-loops instead of doing just an induced subgraph. And then I will kind of contract this subset here, and I will contract this subset into a single vertex and this subset into a single vertex. This gives me a graph, and I want that this graph is expanding. Formally, what I want, suppose that I have an all-to-all flow problem. So an all-to-all flow problem where demand is between edges. So every edge injects one unit of demand. So you could view as I'm placing a vertex on the middle edge, and then this vertex injects 1 unit of demand, and it wants to distribute it evenly to the other edges, including the self-loops. So also the self-loops play in this auto-all flow problem. And what I want is the flow problem being an uniform all-to-all flow problem on the edges here in this contracted graph. This I want to out of some congestion C1. This is kind of the first property. This should have congestion C1. And what is the second property? The second property tells me the following. I have this cluster S again, and I have all these boundary edges. And now I want to have a flow problem where kind of every boundary edge injects 1 unit of flow and distributes it evenly among the other boundary edges. This flow problem has to be solved inside this cluster here. So I could also kind of turn this first into self-loops, and then every self-loop injects 1 unit of flow and distributes it to the others. So this is a different flow problem. And importantly, this flow problem is not on the contracted graph. So here, this flow problem here was on the contracted graph, the first one. This flow problem is on the whole graph. And this I want to solve with some congestion C2. And the claim is the following: if I have this, then I will kind of get a quality that is roughly H times C1 times C2. Okay, so why do I get this quality? So, or how do I prove a quality? The idea of proving the quality is the following. So again, the first direction we have shown, we just now have to show that the cuts in the graph, they are not too much smaller than the cuts in the tree. And for this, what I do is I take any multi-commodity flow that I can route in T with some congestion 1, and then I want to route in G with approximately the same congestion. So sorry, I can route in T with congestion 1, and then in G I may route it with congestion Q. And if I can do this, then it tells me that all the cuts are not too much smaller. And here now I actually have a multi-commodity flow between edges of G. So I have some multi-commodity flow problem, and this is between edges of G. And now what does it actually mean that I have a multi-commodity flow problem between edges of G and I want to route it in T? And I want to, and here each edge sends and receives at most 1 unit flow. And I want to kind of, what does it mean to route this in T? Here I have a graph. So I have a demand between edges. Suppose that I have a demand between this edge and this edge. What does this mean for T? What should I do in T then? And I define it as follows. For T, I'm looking at the path between these endpoints. I'm looking at this path and I'm looking at this path. And kind of in the tree, I want just to connect these paths together. So in order to route this demand 1 from here to here, I just have to kind of maybe establish a path in the tree like this. So this means I'm routing this demand between edges in the tree. I just have to connect the corresponding path. So this has an interesting property if I define it like this. And the property is as follows. Suppose that this is a clustering here. And now I have a demand between an edge here and an edge here. So the edges are in different subclusters. Now, if I alter the demand like this, so currently I have to route 1 unit from edge E1 to edge E2. And now I split this up into kind of, instead of doing routing from E1 to E2, I fix an arbitrary edge here and say, oh, you should instead route here. And for the other guy, I also fix an arbitrary edge and I say you should go out here. If I kind of change the demand like this, the congestion in the tree doesn't go up. Why is this true? So if I look at the tree, how does this picture look in the tree? I have this cluster and I have lots of children. And now what does it mean? I have E1 somewhere here in the tree. So E1 is some path here. E2 is some path here. And now routing from E1 to E2 in the tree would kind of be this. And then down here. And now instead what I do is I want to route somewhere else. I want to route to this edge. But this edge has one endpoint in this cluster and another endpoint in another cluster. So this edge must look like this. It kind of goes, it's kind of a path like this. This goes over this cluster here. And if the same for the other edge. So this other edge must be kind of a path like this, going somewhere in this cluster. But now, how do I route from my edge E1 here to this orange edge? It's sufficient to kind of now my edge E1 is gone. It's sufficient to kind of route upwards to this point here. And also from here, it's sufficient to route upwards to this point, then I will surely meet the other edge. And so then I have routed this new demand in the tree. So I can cut off, and in the tree, the cost doesn't go up. So we'll use this observation in a moment. So now how do I route my demand? Suppose that my demand is routable with congestion 1 in the tree, and now I route it level by level in the tree. And I'm starting with the top. So maybe this is a top level. And what I do is I'm looking at this top level, I'm looking only at the demands that are separated on this level. So I'm looking demands between two edges that are separated at this level. And the first thing that I know is in the contracted graph, I can route with small congestion. This means if I contract all these subsets, I can route with small congestion. But actually this kind of, what I do now is I'm contracting this graph, I'm establishing a path between these endpoints, and then I'm doing uncontraction. I'm undoing the contraction. So this means then I get something like this. The path looks like this. In the contracted graph, it's a path between these two endpoints, kind of. But now in the uncontracted graph, it's not a path anymore because it has a lot of gaps. Now, what I have to do is, in order to route my demand, I have to fill these gaps. So now, in order to route from here to here, I say, oh, I can do this. I will do this in the lower level. I will route this in the next level. So this I explained on the previous part, that kind of doing this doesn't really increase my flow. The flow that or the demand that I have can still be routed in the tree with congestion 1. Now the remaining stuff that I have to route, I have to connect all these things here together. So the light green edges here, they have a congestion of, kind of C1. I can make, or 2 times C1. I can route on the contracted graph with this congestion, all to all. Now, but what I get as a flow problem for such a subcluster here is every boundary edge has kind of some congestion 2 times C1 or so. And I want to route to other boundary edges. So I get a flow problem on these boundary edges. If every boundary edge would send and receive at most 1, then I could route this with congestion C2. But now every boundary edge actually routes 2 times C1, so I will have a congestion of this much, 2 times C1 times C2. So this is kind of the congestion that I need here at this step everywhere. And then for every level in this hierarchy, I get this congestion. And so roughly the quality in the end will be the height times C1 times C2. Now, what is the real problematic thing here? If I want to do this now, if I do a bottom-up construction, it's difficult to get a good guarantee for this value of C2. If I want to get a good guarantee for the value of C2, I'm using a top-down construction. The top-down construction, what I do is you generate a cluster, and then at the time that you generate the cluster, you know that, oh, for this cluster, I can route on the boundary edge. So the value for C2 is good. Here, it's not so good. You cannot get this. It's very difficult to do this bottom-up. But if I only use property 1, I already get a very weak guarantee for this value of C2, namely C1 to the H. And why is this? Because what do I know? I ask how C2 asks how well can I route on the boundary? Okay, but if I can route all to all on these edges here, including edges that leave the boundary, and this is what C1 guarantees me, I can route with congestion C1 here in the contracted graph. Then, of course, in the contracted graph, I can also route between these boundary edges in the contracted graph. So I can route in the contracted graph with a congestion C1 between the boundary edges. But I want to route in the graph S, where don't do any contraction. So what I do is I undo the contractions level by level. So now I undo the contractions, I kind of replace this single vertex by the partitioning on the next level and then put a vertex for every cluster. So I'm undoing the contraction by one level. And now the first level here gives me some congestion C1. So I have to have a float problem on the boundary of this cluster where every edge induces kind of flow of C1. And then I can route this on this contracted graph with congestion of C1. If I would only inject one unit of flow, therefore I get a congestion of C1 times C1 on this graph. So with every undoing of a contraction, I'm kind of paying a factor of C1. So the congestion that I will get in the end is C1 to the H. That's unfortunately very, very bad. Now, what we do is we try to get this better. And we want to put a different value here. We don't want to put the value of C1 here, but a different value. But we still will have this exponential dependency here. So what we do is the following. This is the property 1 as before. Now I'm changing this property 2, and I make this property 2 into a property that just talks about the contracted graph. So this tells me you should be able to route between the boundary edges in the contracted graph with congestion C2 prime. So of course, routing in the contracted graph is a lot easier than routing in the whole graph. So, but if I can do this, then the previous argument as before tells me that I get my value C2 for the real C2 is kind of this value to the H. With every undoing of a contraction, I'm losing kind of this factor once. So now I ask, can we get something where this is kind of an acceptable value? And this we can actually do. So we kind of massage these things now so that this value becomes acceptable. So one natural thing to try to kind of construct such a tree, and this will not work, this is a bad approach, would be using expander decomposition. So expander decomposition, simply you take a graph, partition it into small little expanders so that you cut few edges. That's an expander decomposition. And here in our terminology, I translate it a little bit, it means that you partition it into pieces, this graph here, including the boundary vertices here, is an expander, can route all to all on its edges with congestion 1 over phi. So this is kind of this first property. And you cut few edges. That's an expander decomposition. Now, doing the idea would be do an expander decomposition, contract everything, do an expander decomposition again, contract everything, do it again, contract everything, and so on. This is a way that you want to construct the hierarchy. But now this would be too bad for the second property. So now we change this concept of an expander decomposition slightly. We want to have expanders that are very well connected on the boundary. They only have an expansion of this much, 1 over phi. But on the boundary, they are very well connected. So think of phi as something like n to the little of 1. So the expansion is really poor. But on the boundary, we want that the expansion is a lot better than that. It's kind of 1 over polylog. So now we are given a graph, a parameter phi. And now we partition it into disjoint pieces again. And now we want this. We want this graph is a good expander. Kind of can route with congestion, okay, log m or 1 over phi. This is not so important. What does this mean here? What is this graph? This is an induced graph. So this is an induced graph on UI. And now I replaced every edge that leaves the cluster, not with one boundary edge, with one self-loop, every boundary edge with one self-loop, but with so many self-loops, alpha divided by 5 self-loops. So I'm putting lots of self-loops there. And now I want to be able to route this with small congestion. And I want to cut few edges. This is kind of the same statement as before. And here for alpha, you should think of alpha as, alpha is something like 1 over polylog, and phi is kind of 1 over n to the little of 1. So actually, if I get this, then this C prime, this will be something like this. So why is this 2? So I take this graph here. I take this graph. What does this tell me? It tells me you can route all to all on the contracted graph. So this is a contracted graph. I can route all to all on these edges. But not only this, every edge, every boundary edge is actually weighted instead of with one is weighted with alpha divided by phi. Every boundary edge is worth a lot here. But now this C2 prime, this just asks for the congestion of the flow problem if I route all to all and every boundary edge injects 1 unit. But now this means so here if every boundary edge kind of counts alpha divided by phi, then I have a congestion of log m divided by phi. But now if I this asked what is the congestion if every boundary edge counts 1. So you simply have to divide this term by alpha divided by phi. So this is this. So if you divide it by alpha divided by phi, you get log m divided by alpha. So your congestion reduces accordingly. So this kind of is useful. And actually we can do this, we can construct this. We adapt the result, this expander decomposition, and we can construct this fairly quickly. Okay, so here I have a short argument that proves that something like this should exist, but I will skip this, I think. So what do we get now? If I do this, I use this expander decomposition iteratively. And now what I do is I have to choose the value of phi. and I choose a value of phi in such a way that the height becomes very small. So I'm choosing phi equal to 1 over e to the squared of log n. So what does this mean? If I do this, then this is the height, because if I'm reducing by a factor of phi in every level, the height will now be something like squared log n. So what will be the height? It will be log m divided by log 1 over phi. And now if I put this value for phi, then this will be something like squared log n. And this will now be, roughly e to the squared log n. I'm ignoring logarithmic factors there. What will this be? This will be alpha. Alpha is something 1 over polylog. So this will be something like polylog n to the square root of log n, which is also something like, it will be pretty similar. There will be some log factors sitting out here. So all of this is, and then if you take the product of all of this, then this will be n to the little of 1. So this is how you prove the quality here. And now I just want to very briefly sketch how we do how we dynamize this. And in the dynamization, kind of we lose a lot of other parameters. But the idea is actually pretty easy. And kind of this concept of expander pruning, this was already contained in the previous paper by Zahar, Nowak, and Wang. And what happens here is, so you have an expander. So this is an expander in this expander decomposition. And now what happens is you get edge deletions. And the edge is deleted, another edge is deleted, another edge is deleted, another edge is deleted. So now it may actually not be an expander anymore. You delete a few edges and it's not an expander anymore. But the important thing is, in order to maintain an expander decomposition, you don't have to do this whole thing from scratch. But what you can do is you can kind of cut small pieces out of here. And the remaining thing here will be still an expander with kind of reduced expansion properties. So you cut out kind of something that is proportional to the number of edges that you deleted. And then what you do is these simply become single vertices now. Single vertex is, of course, an expander. And so in the end, so you maintain this expander decomposition by this expander pruning algorithm. And here it's kind of, we had to adapt it to our setting. And in particular, this was a little bit difficult to adapt. But I cannot go into detail where the difficulties lie here in adapting this. But then what do we do for this whole, maintaining this whole thing? We actually maintain the contracted graph. We have G0, that's the original graph, and we have G1, that's the graph that basically is a contracted graph. In G0, you take expander decomposition, and then you contract the graph, that's G1, and then you take expander decomposition, you take the graph G2, G3, and so on. And now what actually happens is that an edge is inserted here, or deleted. Usually say deletion is more difficult. So edges are deleted in here. So you have some expanders here. But what happens is these expanders, they are deleted. So something from this expander is deleted and now introduced as single vertices. But now what happens is actually that, okay, these changes you kind of feed to the graph on the next level. This means that on the graph on the next level, you had these 4 vertices. You had this vertex. These were the expanders in the previous level. And now kind of these additional 4 vertices appear and maybe some edges to these vertices. And so what you can show is that with every level, so you have, if you have I insertions on the first level, on the next level, you actually make I divided by alpha insertions, a few more. And then I divided by alpha squared. So with every level, the number of insertions that you have to handle increases by alpha. But importantly, you only have squared log n many levels. Therefore, kind of you can handle these insertions. Okay, so this is a very brief outline of the pooling process. And okay, what are the open problems here? So the main open problems that I alluded to earlier is this quality is really not nice. You really want to have something polynomial, but it seems difficult to really get this in a bottom-up process. In the bottom-up process, we don't know anything better than this. Yeah, with every step, you get an exponential decrease. So you have to do something like this, where you ensure that the height of this whole decomposition is very shallow. And another open question where would be, can you get guarantees for vertex sparsifiers? So where you do not want to have the guarantee for all vertices in the graph, but only for a subset of the vertices. But then the quality should only depend on the number of vertices in the subset. Okay, thank you very much. Do you have questions?
Thank you, Harry, and feel free to unmute yourself and clap. Always on. Yeah. Any questions? Please just feel free to unmute yourself and go.
Could you maybe elaborate about what is the best? So what would be your objective at the end? What do you think is feasible to prove here?
You mean for the quality, or?
Yes, for the quality.
Okay, of course, there is not. So we have nearly linear time algorithms that can get polylog quality.
Yes. Okay. Do you care about what is the exponent in the polylog?
No. This is we have nearly linear time algorithm to get a polylog. I just talk about nearly linear time. But if I want to talk, if I talk about a dynamic algorithm, we just have n to the little of 1.
Yeah, no, I know, but my question is, so
I don't care about the exponent for now.
Okay, so polylog would be just okay.
I want to reduce this n to the little of 1 into polylog.
Is there any chance to have a lower bound that you cannot do that?
I'm not so sure.
So you expect it is possible to get polylog?
I expect, at least I would assume that the lower one would be pretty difficult.
No, I know there are not too many lower bounds for dynamic algorithms in that sense. So
yes. I would actually, maybe it's possible, but this bottom-up process, this is really the problematic thing, because the only thing that we know is kind of with every level, kind of you lose a certain factor in your expansion, and that's kind of too problematic, too simplistic an approach. But I don't know of anything better. That's the problem.
Okay.
Sorry, I have a question. So if you don't care really about the time, but I'm not sure you know the notion of recourse, which is something that is necessary before you get a good update time, right? So your question, suppose I just want polylog quality, but now just with the solution that doesn't change more than subpolynomial places in the tree after every update. Is that clear that you can achieve that? Or even that is not clear?
Even that is not clear. So yeah, but this is a good question. So basically, don't care about the running time for now, but ask, can you actually get away with a few updates?
Right.
A few changes. But I don't know of an argument for this.
Thank you. And another question is, I guess, in the end, since you said that your result is deterministic, then it means that you didn't really modify Saranurak Wang because that one is randomized, but you probably need this Chusoi at all.
Yeah, okay, but kind of what the thing is that, okay, this all depends on cut matching game.
Right.
And in some sense, we use in our construction, we use the cut matching game as a black box. Saranurak Wang uses cut matching game also kind of as a black box. And now if you just plug in a different version of the cut matching game, you get deterministic results.
I see.
But the results are weaker because the parameters there in the cut matching game are weaker. But they are still n to the little of 1.
Right.
Okay, so thanks again for that wonderful talk. And hopefully I'll see you again sometimes in reality.
Yeah, this would be nice.
Okay.
Thank you, Harry. See you next time.
Yeah.
Bye.
Thanks to everybody.
Yeah, okay, bye-bye.